Good morning. In our previous experiment, we have discussed how to estimate total hardness of water. So, estimate the hardness of water, right? So, today let us discuss the how to estimate the percentage of calcium oxide present in the cement. So, cement. What is cement? Cement is a mixture of. Cement contains calcium oxide, gypsum, iron, silicates of iron, calcium, right? So it contains silicates of magnesium also. So in that we're supposed to estimate only calcium oxide. So this is also an example for complex symmetric estimation. So what do you mean by complex symmetric estimation? In any estimation, if you are using titrant as EDTA, then such type of estimations are called as complex symmetric estimations. In any estimation, if you are using EDTA, then such type of estimations are called as complex symmetric estimations. So today let us see how to estimate calcium oxide using EDTA. So what is cement? So as I told you earlier, cement is a material which binds both brick, stones, right? So brick can it binds bricks to build a wall. It binds silica, iron, stones to form the roof, that is slab or flooring, right? So it's a binding material. So cement is having a good adhesive and cohesive properties. So cement contains, as discussed earlier, silicates of calcium, magnesium, iron, aluminium, etc. So calcium oxide is the prime constituent and later to iron or aluminium present filtrates are precipitate as the respective hydroxide. So how to take? We're going to take 1 gram of cement or known weight of cement and we're going to dissolve it in the acid. So later we're going to add ammonium hydroxide. When you add ammonium hydroxide, the magnesium, aluminium, iron will get precipitated. So later we're going to add ammonium chloride. When you add ammonium chloride, the calcium and magnesium will get converted to their respective chlorides. So here we are supposed to estimate only calcium, but magnesium is also present. We cannot remove magnesium separately. If you are adding something to remove magnesium, even calcium will react and when calcium will be eliminated, because the reactive chemical properties of calcium and magnesium are almost same. So therefore, we're going to remove magnesium during the titration. Okay, so now the cement solution contains what? Calcium chloride and magnesium chloride. Okay, so supposed to estimate that. So what are we going to do? We're going to the calcium, this cement solution is estimated or tried against EDTA solution at 12 to 14 pH using pattern and letters indicator. So let us see how to do this experiment. So as I told you, this is a complex symmetric estimation, so we're going to use EDTA. So already we have discussed the EDTA structure. So instead of using EDTA, we're using disodium EDTA. Why? Because EDTA is painlessly soluble salt, therefore we're going to use disodium salt of EDTA. Disodium salt is completely soluble in water. So EDTA is ethylene diamine tetraacetic acid. So every volumetric estimation contains two parts, part 1 and part 2. So here part 1 is preparation of Na2EDTA. We are going to take W grams of or known weight of Na2EDTA crystals and transfer to 250 ml sample flask. So add 1 test tube of ammonia, dissolve the crystals and add distilled water up to the mark. So this will be shown to you in your demo. Okay, so what do you want to sand solution? So if you know the weight of solute and volume of solid in which it is dissolved, it is called as standard solution. So the weight of the EDTA will be substituted here. It is multiplied by 4 since it is preparing for 250 ml and divided by the molecular weight. It gives you the molarity of Na2EDTA. So later the sand Na2EDTA will be filled in the burette. Conical flask going to take 25 ml of cement solution. Today going to add 10 ml of 4 normal NaOH, which is the mixture of glycerol and diethylamine. So NaOH. We're adding NaOH. NaOH serves two purposes. So NaOH acts as a buffer. Other main reason why you're adding NaOH is it masks the magnesium ion. The filtrate contains calcium and magnesium ion both, right? So in order to remove the magnesium ion or to prevent the magnesium ion in the reaction, in interfering the reaction, we're going to add sodium hydroxide. When you add sodium hydroxide, it will react. Sodium hydroxide will react with magnesium and forms magnesium hydroxide. Therefore, the filtrate contains only calcium now. Okay, when you add EDTA, only calcium ions will get reacted. Okay, so glycerol is added now to get a sharp endpoint, and diethylamine is added to get once again a buffer. So indicator is pattern is indicator, endpoint is wine red to clear blue. So now you might have a doubt. In the previous experiment, also the hard water contained calcium and magnesium. Here also we have calcium and magnesium. Titrant was same, Na2ADTA. But why are we using different indicators? So we are using different indicators here because, so what happens, the pattern, the cement solution, right? So pattern data, the calcium ions, when you add sodium hydroxide, the pH will increase. The pH is 12 pH, right? So at that 12 pH, the erythrom black indicator forms a permanent complex with calcium ions. Therefore, it will not release what calcium ions to react with EDTA. So in order to prevent that, we are going to add different indicator which is stable at 12 pH. That is nothing but pattern reduce indicator. So we are not using erythrom black indicator. At 12 pH, the erythrom black indicator forms a complex with calcium ions which does not liberate any calcium ions to react with EDTA. Therefore, we are going to add pattern reduce indicator which is stable at 12 pH. So by knowing the volume of Na2ADTA consumed, the percentage of calcium oxide, the given cement solution can be calculated. So there is a demo how to perform the experiment. Just have a look over it. Start with the next experiment evaluation of percentage of calcium oxide in cement solution. We're going to take cement. We're going to dissolve the cement as we have discussed in our theory part. So the cement solution is here. We have prepared out 25 ml of cement solution into this. So this we are going to add mixture of NaOH, glycerol and diethylamine. So NaOH is added in order to prevent or mask the magnesium ions to interfering in the titration, and it will allow only the calcium ions to react with Na2ADTA. So glycerol and diethylamine is also added. Glycerol is added to get a sharp endpoint, and diethylamine is added not to act as a buffer. So we will add 5 test tube of this mixture, NaOH, glycerol and diethylamine. We will add half test tube of this, okay, to this mixture, and we have taken 25 ml of cement solution. So we are going to add pattern reduce indicator over here. This is pattern reduce indicator. So as we added in our previous experiment, the erythrom black indicator, when here we are going to add pattern reduce indicator, beams of pattern reduce indicator. So when we add pattern reduce indicator, we get same white red color. So this white red color we are going to titrate until we get clear blue color. So the experiment is performed until we get clear blue color. You can see the titrating to get until clear blue is obtained. Since glycerol is added, we are going to get sharp endpoint. Diethylamine is added in order to maintain pH about 10. Since diethylamine is added and pH is about 10, we cannot use erythrom black indicator in this experiment. Staging and clockwise stop. So once you get this endpoint, stop the experiment. Okay. Our titration, the endpoint what volume of Na2ADTA was consumed around 8.5. So concurrent volumes are obtained. So suppose calculate the percentage of calcium oxide present in the cement solution. The calculation is 18.5, and that's the XML of Z normal molar EDTA plus 18.5 ml of 0.02 molar requires 18.5 into 0.02 into 0.05608 or amount of this one. So we get 0.0207. So in order to find out percentage of calcium oxide into 50 cc of cement solution, we have the formula 10 into 8 100 divided by W dash. Where W dash is the weight of cement taken. We have taken 0.3 grams of cement to prepare the cement solution. So the preparation of cement solution is already discussed earlier before demonstration. In the substitute this, we get 69%. The cement solution whatever we have taken should contain oxide. So similarly, we can determine the percentage of calcium oxide present in various cement sample by volumetric estimation using Na2 NADA. Thank you. Thank you.